Find parametric equations for the line through the point 0, 1, 2 that is parallel to the plane x plus y plus z equals 2 and perpendicular to the line x equals 1 plus t, y equals 1 minus t, and z equals 2t. So we need two things to find parametric equations for a line in R3. One is a point on that line, and we have that at 0, 1, 2. The other is a direction vector, a vector that tells us the direction of the line, and we're going to use the other information to find that. Suppose I got my plane right here, and I want my line to be parallel to that plane. So let's suppose the orange line is the one we're trying to find the parametric equations for. And suppose that this orange line is parallel to that plane, but let's suppose it's also perpendicular to this green line here. Now, the green line, we'll suppose, intersects it like this, but we know it's going to form a right angle with it. Well, if we know the direction vector for the green line, which we do, let's say that that's this vector, I'll just draw it here in red, and let's call that vector u. Let's suppose that's the direction vector for the line we were given that we want to be perpendicular to, and we know a normal vector to our plane, which we can find based on the equation of the plane. Then the direction vector for the line we're trying to find, which we'll call v, is going to be orthogonal to both u and n. It's orthogonal to n because the line is parallel to the plane and thus orthogonal to its normal vector. In fact, if I were to slide that vector n up here like so, you can see that the vector v is going to be a right angle to n as well. And if we take u cross n, putting our right fingers down u, curling them up towards n, our right thumb is going to be going in the direction of v. So you get the idea of what we need to find here. So let's let u be the direction vector of the line that we are given. Now we are given the parametric equations for a line, and so the direction vector, or a direction vector, is given by the coefficients of that parameter. 1, -1, and 2. Our vector n, a normal vector to our plane, can be given by the coefficients of x, y, and z when our plane is in this standard form here. So 1, 1, and 1. And so now a direction vector for our line, which we're going to call v, is going to be found by taking u cross n. And so that'll be the determinant of this 3x3 matrix with I, j, and k across the top row. We'll put the components of u across the second row and the components of n across the third row. So this is I times the determinant of the lower right 2x2 after we block out the column and row of I. That's a -1 minus 2, main diagonal product of -1 minus 1 times 2, which is 2, minus j, so always negative j here. Now block out its column and row. We're left with a 2x2 matrix. Its determinant is 1 times 1, or 1, minus 1 times 2, which is 2, plus k, and block out the column and row of k, and take the determinant of the 2x2 that's left here in the lower left corner. 1 times 1 is 1, minus 1 times -1, which is -1. And so what do we get here? A -3i. Let's see, that's a -1 times a negative j is going to be a positive 1j, or just positive j. And 1 minus -1, that's 1 plus 1, or 2k. In component form, -3, 1, 2. That's a direction vector for our line. Once we got that, then we're in business. We have a point on our line. Say we have the point right here at 0, 1, 2. And what we do is pick any other point that we want to be on our line, some point out here, x, y, z. And we form a vector from the point we know is on our line to any point x, y, z that we want to be on our line, and that vector has to be parallel to the direction vector v. So that vector is given by x minus 0, y minus 1, z minus 2, and I want it to be parallel to v, so it has to equal some scalar multiple, and I'll go ahead and use t for the parameter of this line I'm trying to find, even though it's already been used in this problem for the parameter of the given line, but that's okay. It's going to be t times a direction vector of -3, 1, 2. And so x is equal to -3t, y minus 1 is equal to positive t, and z minus 2 is equal to 2t. And so our parametric equations then are x equals -3t, y is equal to 1 plus t, and z is equal to 2 plus 2t. Now, if you cross your things the other way, we can just point that out. If you took v to be in cross u, you'd have got positive 3, negative 1, negative 2, and the parametric equations just would have been x equals a positive 3t, y equals 1 minus t, and z is equal to 2 minus 2t. So either of these forms is okay, it just depends on how you did your cross product of your direction vector of the given line with the normal vector of the given plane.